Chapter 4 throws us a curveball here. Up until this point, we've been trying to fit a curve to data, quantitative data, and now suddenly they're going to throw categorical data at us. So let's try to remember what categorical data is and how it's different than quantitative data. Categorical data is you are in one specific category, you're not. You're a boy or a girl, yes or no. They're not asking me my weight or my height, which would actually have a number associated with it. You're in a certain category and you just count how many are in that particular category. All right, whenever we have categorical data and we have different variables, I've got an example up here on the board. A study was done and they studied 2,773 young adults. Their ages were 19, 20, 21, and 22, and asked them where they were living. Okay, so we've got two different categories working here, where they're working and what their ages are. We want to create something called a two-way table. Right, the first thing that you always want to do when you get a two-way table of data is to fill in these totals. I've already done that here. Quite often you'll just get this 3x4 table. The first thing you're going to always want to do is to create the total here that live with their parents, the total that live in someone else's house, and the total that live in their own house. And you want to do the same thing for the ages. So the first thing that you do when you get categorical data and when you have two different types of variables and many different types of things in those variables is to create something called a two-way table. All right, one of the first things that you'll do with this two-way table to try to investigate it and see what's going on is you'll be asked to create what's called a marginal distribution. Marginal distribution is you're just trying to get an interpretation of what this table is telling you. For example, if we would like to know where the students live, when you're doing a marginal distribution, you're going to be dealing with the totals number. Okay, in this particular case, I want to know where students live. So these are the three different options I have for where students live. So to find the marginal distribution, I would take these particular row totals and put them over the grand total. For example, of our 2,773 kids, 48.9% of them are still living with their parents. So marginal distribution, I want to take the row total and put it over the grand total. Percent that are living in someone else's house, okay, that would be the total here, 162 over 2,773. And then the percentage that live in their own house, that would be the 1,254 divided by 2,773. And these are the associated percentages for those. Now this book goes crazy and gets all fired up about, well, shouldn't these add up to 100%? If I look at these, they don't add up to 100% right now. I think it's 99.9%. Why don't they add up to 100%? That's just rounding error, so don't freak out about that. They should add up to 100%. These are all the 2,773 people. If you're asked a question on your homework, why don't they add up to 100%? Well, that's just a particular rounding error. So, if I'm doing a marginal distribution, you can find out the marginal distribution percentages, and then what do we do with categorical data? We can create a bar chart for those various categories. So the title of this one would be Where Do Students Live? These are our three categories, and these are associated percentages that go with them. So when I look at the marginal distribution, I can see that overall students are living with their parents and on their own in a far greater percentage than students that are living with someone else. Now, I could also have done a marginal distribution on age. Okay, in which case I want to know, hey, what percentage of the students are 19? That would have been the 477 over the 2,773, 704 over 2,773, and I could have created a graph for that. So those are two types of marginal distributions I could have created from this data. But if we want to go a little bit deeper, we're going to create something called a conditional distribution. And through a conditional distribution, we can get some sort of a relationship from this categorical data. And what do I mean? This is generally how a conditional distribution will be asked. Given someone is 19, where do they live? So in a conditional distribution, I'm only going to be looking at one of these columns or one of these rows at a time. So for a conditional distribution, if I want to know, given someone's 19, this is all the people that I care about. Once they say that, okay, given someone's 19, this is the only column I'm interested in this problem. Now, given they're 19, where are the 19-year-olds living? Well, I can just calculate those probabilities. In this case, it would be 324 over 477 are living with their parents. Almost 68%. What percentage of the 19-year-olds are living with someone else? That's 37 over 477. That's almost 8%. And then what percentage of the 19-year-olds are living in their own house? That's the 116 over the 477. So again, marginal distributions, you're going to be taking the row or column totals over the grand total. But for a conditional distribution, you're only going to be looking at one of the rows, or one of the columns, or one of the rows. If I'd have asked, given they live in someone else's house, what's their age? I would only be focusing on this row, these 162 people, and the percentages we're looking accordingly. All right, then they'll ask you to draw a graph of that conditional distribution. So this particular one, given they're 19, where do they live? Okay, these are the percentages we got here. And you'll notice kind of a difference over here. The younger students, this kind of makes sense too, right? They're younger, they're 19 years old, they have a higher proportion that are still living with their parents. So we go a little bit deeper into the number and describe a relationship. The relationship, it appears that the younger they are, the more likely that they're living with their parents. Okay? So you're going to be asked to do several marginal and conditional distributions. I'm going to want to see the graphs. Okay? And don't forget, when you make your table, I want to see the row and marginal totals put in first. All right, the next thing we're going to talk about is this thing called Simpsons Paradox. If you want to win a lot of money on a bet, Simpsons Paradox is the way to go. Honestly, if somebody would have asked me this question I'm going to ask you right now, I'd have gotten it wrong. Here's the situation. Let's say, let's do a football situation. Let's say I've got two quarterbacks. I've got Peyton Manning and I got Tom Brady. And they both play in their first game. And in the first game, make sure I have to say, in the first game, Peyton Manning has a higher completion percentage than Tom Brady. Now, completion percentage means how many passes I completed over how many I attempted total. Okay? So in the first game, they play a game, Peyton Manning has a higher completion percentage than Tom Brady. In the second game, Peyton Manning again has a higher completion percentage than Tom Brady. So in game one, Peyton Manning was better. In game two, Peyton Manning was better. Now, is there any way in the world that if I combine these two games together, that suddenly Tom Brady would have a better completion percentage? Is that possible? I mean, think about this. Manning's better in the first game, completion percentage. Manning's better in the second game, completion percentage. But I put the two games together, suddenly Brady's got a better completion percentage than Manning. I want you to think about that for a second. Is that possible? Okay? Can I do better? Can someone do better in the first game and second game, and then all of a sudden you put the games together, he's doing worse? Games together, and suddenly you've got a better percentage than me? It'd be like on one test, I did better than you on the first test. And then I did better than you on the second test. But now we put our grades together, you got a better grade than me?
It depends on how well you did first and second. No.
Well, I did better than you on the first test, I did better than you on the second test. Now we put our grades together, you got a better grade than me?
You get like a, I don't know, like a 64 and like a, you know?
Well, I mean, I don't know. Could that be? I mean, you do better than me on the first test, you do better than me on the second test. We put our test grades together, our overall grade, and I got a better grade than you now?
Oh, percentage?
Yeah.
Oh.
Well, let me give you another example. Okay, excuse me, you all sitting out there saying, yeah, that can happen. Well, let me give you this example then. Okay, you and I are taking a test. I do better than you on the first test. Okay. I have a better percentage than you on the second test. Now, we're going to put the two tests together and put our grades together. Is it possible for you to have a better percentage than me? Is that possible? The answer is yes. Okay? This is called Simpsons Paradox. Let me give you the example of those two quarterbacks again. Okay? All right, what I've got here is a couple of two-way tables. B stands for Tom Brady. M stands for Peyton Manning. This is the number of completions that Brady had in game one. He completed 9 passes. He incompleted, that's not, symbol for not. He didn't complete 9 passes, so he was 11 for 20 overall. So Brady's completion percentage in game one is he completed 55% of his passes. However, Manning in game one completed 3 of his 5 passes. So Manning in game one has a higher completion percentage than Brady. All right, let's go to game 2. In game 2, Brady completed 1 of 5 passes, only 20%. And in game 2, Manning completed 6 of 16 passes, which was 37.5%. In game 2, Manning again has a higher completion percentage than Brady. So in both of the first 2 games, he got a better grade on his test. But we put both games together. If I put both games together, Brady completed 12 passes of a total of 25, and Manning completed 9 passes of the total of 21. When I check the total percentages out, Brady's completed 48% and Manning only 43%. This is known as Simpsons Paradox. There's a lurking variable here. We talked about lurking variables a couple of days ago. There's something going on underneath that's causing this to happen. And what is it? It's the actual sample size. Take a look here. This is what you've got to be able to discuss for me on your homework and your test. You need to talk me through this, how this can work in whatever example that you have. In the first game, Brady had a pretty high completion percentage, much higher than the second game. But notice he had a lot more passes at the 55%. So when we combine the 55% total he had in the first game and the 20% total he had in the second game, when I combine those two, which one are they going to be closer to, the 55% or the 20%? And the answer is the 55% because I had a higher sample size here. So the overall average, as you can see right here at 48%, was closer to the 55. This had a greater weight to it. Now, notice Manning. Manning was just the opposite. When Manning threw for the high percentage, he didn't throw very many passes at all. But when he threw for the low percentage, okay, he threw a lot of passes. So when I combine these 2 games together, where's the overall percentage going to be? Closer to the 60% or closer to the 37%? Well, this one carries a greater weight. So the overall percentage is going to be closer to the 37%. So when I combine these 2, it's not right in the middle. If they'd have thrown an even amount of passes, then the average would have been right in the middle. But since they threw more passes here, when I do the overall average, notice that the 42% is much closer to 37 than it was to 60. So they were kind of going in opposite directions. When we combined the 2, it got the 2 for Brady got closer to the 55, and we combined the 2 for Manning, it got closer to the 37.5, and they just switched directions. So that's Simpsons Paradox, and the lurking variable here was the size, the number of passes for the different percentages. Okay? You have to be able to describe that. All those words I just said, 20 passes here was greater than 5, 55%, the overall went closer. That's what you have to describe on your homework problem, and then you're going to have a question on your test that's going to ask you to describe this phenomenon.